Thanks, Malcolm. All right, so everyone on Zoom hears me, I hope. Okay. All right. Hi, everyone. I'm Behtash Babadi. I'm from the EC department here at the University of Maryland, College Park. So I really appreciate you guys being here because I know I'm standing between you and crab cakes in Annapolis. So just gonna, hopefully make it fun so it doesn't bore you too much. So I'm going to talk about some of the recent data analysis methods that we've been developing in my lab, in particular an application to auditory data from multiple data modalities from my collaborators, all through the so-called Granger formalism. So I'm going to talk a little bit about that. This is joint work with an amazing group of current, former students, collaborators that I would like to acknowledge here. So just a quick flashback to CogHear 2023. So back then, I was looking at a problem that had nothing to do with the Granger formalism, but it's a good refresher because I think if any of you are interested in collaborating about this, I know some people are, so we can talk about this offline. So the key question that I had was whether we can achieve near 100% accuracy in decoding in AAD applications in practice, all right? So you might wonder what that question is, but years ago, decades ago, Shannon, Fano, and information theorists talked about this exact question for communication channels. So my student Aranthi is sitting back there. So she actually developed a model of AAD based on a communication channel. So in fact, you can have a binary communication channel in which the brain is in either the state 1 or state 2 or code word 0 and 1, depending on the attention to speaker 1 or speaker 2. And this state is being transmitted in a noisy channel that we call EEG, let's say. And then using techniques from information theory, Ruwanti showed that, for instance, if you want to achieve 1 bit of mutual information, which is perfect recovery of whether speaker 1 or 2 attended, at least in a realistic simulation, we need about 30 seconds of data to really reach the capacity. Also, Fano's inequality, famous inequality information theory, showed us some other interesting thing, that there is a lower bound on the accuracy of AAD, in the sense that no matter what method you use, you can never have an error probability that, let's say, goes below this line, depending on the data length that we have. For instance, if you only have 2 seconds of data, you can never have an accuracy better than 80%, right? So it gives us an unachievable area. And Rubanti did this great work, and she was actually a finalist of the Best Student Paper Award at Asilomar. Top 8 out of 500 papers. It was really exciting, but we kind of left that line of collaboration. But recently, in a conversation with Nima, we thought, okay, after Shannon's theory, communication theorists and practitioners have been really focusing on this achievable region, right? So Fano tells you that the red region is not achievable, but a lot of coding theorists tell you that let's focus on the achievable part. And there are lots of techniques developed in communication theory how to achieve that. So Nima and I have had a couple of nice conversations about that. Hopefully we're gonna pick up on that. So who knows, maybe by next CogHear, we're gonna tell you some nice story about the green area that is what we can achieve really. Okay? Can that lower bound be achieved or not? Okay. All right, so now flash forward. Again, if you guys are interested in this line of work to find fundamental limits of AAD performance on how we can achieve them, I'm really happy to talk to you about this offline. So again, this slide is taken from the same talk I gave 2 years ago in CogHear. So that just gave an overview of Granger causality. So the concept is very well known and basic. So imagine you have 2 time series x and y. We want to test whether we can improve the prediction of x by having some knowledge about the past of y. If there is an improvement, we say that y has a Granger causal or GC effect on x. So in pictures, let's say these are 2 time series x and y. Once I test the model that I want to predict the future of x based on its own past. So I have a lagging window. I move it along my data. I try to find a filter, let's say, a TRF type filter to predict the future of x. I call that the reduced model. And it has an error variance sigma r. Now, next time, I also include the history of y and x together to predict x. I do the same thing. Now I have a richer model now because I have more covariates. I call that the full model, and it gives me a different prediction error. Let's call it sigma square f. The log ratio of these two variances is what people call Granger causality. In other words, the improvement in error prediction when you have more covariates. Okay? So this is well known, from the times of Norbert Wiener, and Granger himself won the Nobel Prize actually in econometrics because of some related work to this, the integrated prediction model and all that. And it has found its way in neuroscience, as you're aware. But if you look at the literature, there's a lot of evidence and papers that show you that if you apply Granger causality off the shelf, as Granger perceived it, to neural data, it most likely fails. So I cite one reference that shows a lot of pitfalls of Granger causality in practice. So over the past decade, I've been really trying to rethink the Granger formalism when it comes to analyzing neural data. And there are three problems that we've been really focusing on. The first one is that in neural data, oftentimes we have limited short and non-stationary data. And if you try to apply the method I just showed you, you either overfit or you underfit. That results in false alarms and misses. The second problem is that there is a lot of nonlinearities, and oftentimes the observations are indirect. Let's say MEG and EEG. You want to talk about, let's say, some Granger causal effects in the cortex, but you can't really measure the cortex. You just have an indirect low-dimensional observation of it. Also, there could be non-Gaussian data and latent processes that you don't see. The third one, which is a more philosophical fundamental question, is the effect of correlated input, right? So if there are two inputs driving two sources, you might mistake a causal link between them, whereas the latent input was really driving them. I'm showing a list of papers related to answering these questions. It goes back to 2016, almost a decade long, worth of effort. So you see some familiar names. So, Shihab has been in some of these works, Jonathan, Lucas Hara and his group, so several others in this conference. But I want to rephrase a quote from George Box, a great statistician that you guys know. So GC is a model selection procedure for network data. So that's my part. It's not George Box, right? But all models are wrong, and if you use them carefully, hopefully they're going to be useful. Okay, so that's the message I want you to have in the back of your head as we go forward. So I'm not going to talk about causality. I'm not going to talk about synaptic connections, direct connections between sources. What I'm going to show you is that Granger causality is a model selection. Select some models that I'm going to argue hopefully are going to be useful. Okay. So I'm not going to talk about all those papers. I'm just going to give you a brief overview of the more recent ones that are after CogHear 2023, pretty much. So let me start with the first one. So this framework was done in collaboration with Jonathan Simon, and we came up with a way to apply Granger causality on cortical data, even though you're observing the cortical data indirectly using things like MEG. And what we used was some theoretical underpinning based on sparse log likelihood estimation. And what I'm going to show you is that the usefulness of Granger causality in this case is that it adds another dimension to the so-called functional connectivity approach that is commonly used. So if you think about trying to come up with a network description of cortical activity, the typical approach that people do is a two-stage approach. So you first try to source localize, let's say, MEG onto cortical sources. I call that stage one. And in stage two, I'm going to apply Granger's method to the sources that I found. There are many pitfalls associated with this approach. I've listed at least 4 of them. So there are lots of biases that are placed in favor of source localization that propagate to the stage of network inference. There's the issue of temporal leakage. You lose some spatial resolution, or you gain and lose temporal resolution. There's some sensitivity to patch statistics and all that. So my student my late student, unfortunately. Some of you from 2023 might remember Behrat. He's not with us anymore. But what he did was to come up with a nice one-stage approach to really solve this problem without going first to source localization and then finding links. Beautiful statistical framework. I'm going to talk a little bit about it. So here's a toy example that shows you if you have a ground truth connectivity, top left, the network localized GC or NLGC pretty much hits it. But if you use the approaches that are two-stage, first source localized and then try to find connectivity, you see we get a lot of false alarms. That's why off-the-shelf application of GC, as I said, is very problematic. So you really need to carefully fix things there. So one main component of all this that we've been looking at is the so-called dimensional reduction of the cortical space. So those of you who have worked with source localization, the idea is very simple, how to come up with a distributed source model. So I take an icosahedron, it has 12 vertices. I subdivide each triangle, and I do it a bunch of times, and I get a dense set of vertices. Then I can place it on the cortical mantle, one on the left hemisphere, one on the right hemisphere. Those give me the distributed sources. If you do it 7 times, you end up with about 300,000 sources, which is crazy. We can't really hope to estimate that many with MEG or EEG. But one idea is to find these so-called Warner regions in any of these source spaces that give us these so-called cortical patches. Now, if you zoom in into one of these patches, so this is figure created by Rishab, so sitting right there. So one of these cortical patches, you see it has tens or hundreds of dipoles, each of them directed somewhere, right? But if you just do a SVD and take, let's say, the top 3 modes of this set of dipoles, you can see that most of the variance of all these dipoles producing MEG for you can be described by these 3 components. In other words, this collection of dipoles sitting on one part of the cortex can be very well described by having one dipole in this direction, another in this direction, and a third one, right? And this gives us a huge amount of dimensional reduction that we've been using. And that allows us to talk about eigenmodes of activity as opposed to sources of activity. And then over those eigenmodes, we can come up with a, let's say, state space model. So we have observations of MEG. And we have a model of how the sources evolve in time. And then we do the same exercise as Granger told us to do. We have a full model that looks at the log likelihood of the observations of the states given the observations. We have a reduced model that takes away the contribution of one source to another. We compare them. We subtract the log likelihoods. We do some bias correction. I'm not going to go into too much of the details. And we get a statistic. So we get a statistic that I call D superscript dB, or the bias deviance of source J to I. That gives you a number that kind of looks like the strength of the connectivity between 2 nodes, I and J. I'm sorry, bias again? Yeah, so the debiasing is that there are 2 functions that you need to find from data and subtract and add to debias this. And the reason is that we're using sparse estimation, so there is an L1 norm regularization here. So as opposed to ridge regression that you have an L2 norm, here we have an L1 norm. And that biases your estimates because you get sparse estimates. So for sparse estimates, the Gaussian confidence intervals and all that goes away. We don't have that. So you need to correct some bias so you can recover some Gaussianity and be able to come up with meaningful statistics. So those are the bias terms. And then when you do that, you get a statistic that tells you how strong the connectivity is. I don't know what that arrow is doing there. But yeah. So now let's say I get a value of 0.15 or 10 or 237. So can I say the link exists between these sources or not? So what Behtash showed was a really strong statistical testing framework, which tells you that if there is no GC link, this statistic that we get, this DGB, is distributed according to chi-square with degree m, and m is exactly the number of parameters that is the difference in the full model and reduced model I told you about. So it's a number that we know. But if a link exists, then we get a non-central chi-square. So it looks like a chi-square, but it's kind of shifted or skewed. And now we have a null hypothesis. We also have the alternative hypothesis. So this is one of those cases that I really like, because oftentimes you only know the null hypothesis and you try to find the p-value. Here we also know the alternative hypothesis. So we can find both the p-value and also type 1 error, right? So we can have type 1 error, type 2 error, and we can come up with a stronger statistic, which we use here, the Udin's J statistic, which is 1 minus the false alarm minus the true rejection. So we get a nice statistic. So the closer this number to 1, you have a stronger confidence that there was a link between those two, and otherwise you don't. So now you might wonder, all this fancy bias correction, as Jonathan was saying, or sparse estimation, is it necessary or not? So a few years before, I was working with Patrick Canal on a different problem in 2-photon data. And we tried to use a similar framework. And one of the reviewers asked us the same question, that why are you using such fancy math? Do you really need to do all this? So we added a simulation, which is now in the supplement of the paper. Here's a simple case. You have 8 neurons or 8 sources, and I'm showing you the activity. And there's a ground truth network between them. So if you don't use any sparsity or any bias correction, this is a network that we estimate. So you see there are false alarms compared to the ground truth. If you don't correct for the bias, then you're underfitting. So you see we're missing a whole bunch of things. But when you do sparse estimation and bias correction, we exactly recover the network. So essentially, the bias correction increases our statistical power, and it's necessary in a sense. And sparse estimation reduces chances of overfitting. So they seem to be necessary components of this approach. There are more realistic simulations here that I'm going to skip through that shows that this approach, the NLGC, does much better than the two-stage approaches. So let me skip that. Let's get to some data. This is data from Jonathan's lab, subjects listening to 5 hertz tone pips, and also in a resting condition. We wanted to see what happens in terms of the so-called GC network or NLGC networks in the brain. So we also had younger and older participants. So the top row is younger, bottom row is older. The left-hand side is the grand average of 22 subjects. The right-hand side is just a representative, 2 representative subjects, one older, one younger. So the interesting thing that I want to show you first is that imagine I wanted to do functional connectivity the way people do. Then I would get this grayscale image, because now the notion of directionality is lost. But with Granger causality, you see we have color now, because now we know which links are going, in this case, from frontal to temporal cortex or vice versa. So here, red links are the ones from frontal to temporal. Green links are the ones from temporal to frontal. So immediately off the bat, you can see the advantage of having a directional measure. And in this case, if I put these links in terms of the number of counts and a graph and do some statistics, this is mixed effect models, but I'm just going to tell you what the message is. Something interesting that we see is that in the delta and theta band, during the resting, both for younger and older, the topology of the network in terms of NLGC looks very similar. So there's stronger temporal to frontal, some frontal to frontal, some parietal to frontal. But during tone processing, things change. So the connection that in the rest was parietal frontal is now frontal parietal. The connection from temporal to frontal is not much weaker here. It's mostly frontal to temporal. And in the older cohort, we also have a lot of internal parietal connectivity that doesn't exist for the younger. So the story becomes even more interesting for beta. So just immediately looking at this, you can see that there is a lot more blue down here, right? There is more green elsewhere, but there is a lot of blue down here. Again, if you use functional connectivity, you lose all that coloring. But now with NLGC, we can distinguish the origin of, for instance, here, frontal to parietal or parietal to frontal links. So again, after doing a lot of stats, we see more interesting both age-related and condition-related changes. In the resting, again, the networks between older and younger are more similar, but during tone processing, in the younger, you see a lot of frontal to frontal and parietal to frontal and temporal to frontal. So it looks like frontal lobe is heavily involved as receiving information from all areas and doing some processing. In the older, many of those vanish. So you see a lot of frontal to parietal, and not much connection between temporal lobe. So this is all in beta band. Okay, so I'm just going to go through a couple of math-heavy slides, but hopefully it is worth it, because I want to tell you that all of this has a strong theoretical underpinning behind it, in the sense that what GC is telling us and how we can use sparse estimation to find it has some underpinning. And my former student, Prolay Das, who's now an assistant professor at National Brain Research Center in India, he tried to study the problem of Granger. Again, two-time series X and Y. There is a lag of P in the past of these two-time series over which they interact with each other. And imagine there is a correlated input to these. So in other words, this W could be the confounder that makes us find a false link between X and Y, right? And we assume that the connection or the interaction between these two processes is through a sparse set of lags. For example, in your TRF, you know that certain lags are important, but there's only few lags in the filter that connects or models the interaction between these two time series. So we assume it's a sparse parameters, and we use L1 regularization as opposed to ridge regression to find these parameters. And Prolay came up with a statistic that is similar to Granger's statistic. Instead of taking the log ratio of the variances in the two cases, we take the difference over the larger one. And he proved this beautiful theorem. I'm going to show you the informal version, which is, I think, more interesting. The theorem really tells you that it is possible to reliably identify GC by a careful choice of the regularization parameter if you have strong enough effect size and if you have long enough observation. Okay? So it might sound trivial, but what is interesting is that we can really quantify the fundamental limits of GC. Remember I told you these two sources, the W, X, and Y, the confounding sources that are making us make a mistake. Imagine that the eigenvalue of the covariance between them is delta. So if delta is 0, it means that these two are exactly the same, right? So it's a rank efficient matrix. But if delta is really small, it means that these two confounders are very similar, so they can make you make a mistake. So what this theorem tells us in this constant, we need to have number of observations scaling as 1 over delta square. In other words, if you want to have a hope that you can get away with confounders, and if the confounders have this really small delta, then the number of observations you need should be proportional to 1 over square of delta. So that's what I mean by fundamental limits. Obviously, if delta is 0, in other words, the confounder is exactly deriving this to the same, there's no hope of finding GC. But this gives us hope that there's a graceful regime over which we can identify GC. All right, so again, this is a simulation that Prolay did. Again, let's say we have a confounder, Z, that's driving X and Y, but there is a true link from X to Y, but not from Y to X. But the way we organize this confounder is that this process Z is deriving Y earlier than X. So potentially you would see a false link between Y to X, but that's not a true link. It's just because of the confounder. We see that when you do sparse estimation and use the theoretical testing threshold that we do, you can exactly see that if you have long enough observations, the non-existent link, the red one, goes below the threshold and the existing one goes above. Whereas if you don't use sparsity, actually they both blow up. So the two curves overlap. There's no hope of identifying the true versus the confounding link. The same with the number of lags. So if you have two processes that are connected with a large latency, again, we can recover that pretty robustly, whereas the non-sparse estimate doesn't have any hope there, right? So again, we verified this in simulation also. Now let's go back to NLGC. So we tried to apply this for data from different contexts. So this is a cartoon of the result that we got in collaboration with Liz Marsh at Hopkins, neurologist at Hopkins. to look at how networks between motor cortex and elsewhere in the brain change as a result of post-stroke rehabilitation, right? So the list had patients coming in, first visit, then 6 months later, second visit, we took MEG, we looked at the connectivity, and we actually saw that, over this, good cohort of patients that we had data from, you see the interesting change, bidirectional change from motor cortex to the rest of the brain and vice versa as a result of rehabilitation. Right now, with Rishabh sitting there, Rishabh took NLGC to the next level, so he included many more interesting facets to it. And now we are looking at auditory processing in healthy aging. So his poster is right there. So I took these images from the poster, the second poster over there. So these are 13 younger and 9 older adults listening to, 3 types of stimuli: speech and quiet, the 2 CogHear condition where the mask care and the target have a 0 dB SNR difference, and the more severe case that they have a -6 dB difference. So in the delta band, again, the interesting thing is that throughout the deteriorating noise condition, you see there's more frontal to frontal connectivity in younger than older. In the older, there's some parietal frontal connectivity, and then as noise gets worse, there's more temporal to temporal and temporal to frontal connectivity in delta. Kind of similar story in theta with slight differences. But again, this is something that we're fine-tuning right now, but this is just our preliminary results. That brought us to another question. Go ahead.
Just trying to get a feel for how these connectivity measures might vary between participants or between groups. So I can obviously think about ERPs or TRFs or something. You often see stronger TRFs in older people whose hearing is not as good. And we often like to try to think that the speech tracking should be better for some speech, for example. And a lot of the inter-individual differences I think about are just biophysics, right? Someone's cortex is a certain way. So doing inter-individual things like that, R values for my predictions across people, and I got performance and some behavioral paradigm across people. I don't find correlations that often because a lot of variance is just biophysics.
That's right.
But here, I'm just trying to get a feel for the same question across people here. If I'm getting multiple measures of the same person, maybe, and I'm trying to find, how strongly connected they might be. Do those same biophysical inter-individual differences also confound those kinds of, like in the stroke study, these connections getting stronger? Was that also true for the subjects who improved the most in the rehabilitation, for example?
Yeah, that's a really good question. So we have that analysis in the paper. I didn't put it there. Yes, it does. Yeah. So we saw some correlation with that. But the interesting thing, if I remember correctly, was that it wasn't exactly intuitive that because there were some certain scores of cognitive improvement and motor improvement that the neurologists get. Not all of the scores, the improvement in the scores were correlated with that, but some of them were strongly correlated. So that was another interesting finding. So for the second question, another answer I want to give you is that in the realm of MEG, the inter-subject biophysics variability is a little bit more mitigated because of the magnetic permeability compared to the electric properties of the skull and scalp mass. So I think some of the let's say skull scalp type of variability is mitigated in MEG, but not always. So yeah, but there's some. But I'm going to show you some TRF. So actually looking at the older, younger TRF might give us some clue about that too. Yeah. So and in an earlier version of this work, we got some question, again the confounding question that Lucas was also talking about a couple of days ago. So imagine that there's a talker, and that's the speech, let's say the source, and I have 2 cortical areas A and B, and imagine that there is a TRF that is predicting that, or let's say producing the activity of source B and A, and the TRFs are delayed versions of each other. So in other words, this TRF is an earlier version of this one. So as a result, the brain activity looks like this is an earlier version of this. In other words, we might see that there's a connection from the region A to B, whereas this connection doesn't exist. It's just because they're both driven by stimulus, right? So in other words, if a confounding source, or in this case, it's not really confound, it's what we know is their stimulus. If it's driving these two sources, could it result in a false link between them? So what Rishab did was to actually, compute TRFs. In this case, I'm showing you, so the older is blue, younger is red. And this is for the attended case, unattended, and the mixture. The left column is the envelope, and the right column is the envelope onset. So you see the typical things that we expect. So in fact, we can see the nice stereotypical TRFs. There's definitely some differences in older and younger, as Ed was mentioning. So there's definitely some age-related stuff going on. And they localize nicely to areas that we expect them to localize. So again, these are the cortical sources that show significant TRFs. But what we wanted to test was whether the GC links that we see in the brain are confounded by the fact that the two sources are being driven by the stimulus or not. So what Rishab did was consider 4 possible cases. Either source A is connected to B and the stimulus has nothing to do with them. Or the stimulus is deriving source A only and A derives B, or this case or the confounding case. So case 4 is the problematic case. And we counted all the links, hundreds and thousands of links across all these objects. And we actually see that it's not the case. We don't see many more such links compared to other categories. They're pretty much flat. In other words, it looks like whether a source is driving A or B doesn't have anything to do with whether A and B are linked together or not. So our immediate answer to this is that it doesn't seem like the stimulus is confounding the links that we're finding. So around the same time, I had a conversation with Lucas. And Lucas said, I know Ed and others like TRF, and you like the other way around. You don't want to include the stimulus. You just want the history of the process. So why not doing it together, right? So we started looking at this VARX type model. So Lucas had a really nice talk about this. I'm just gonna, again, briefly go over some of the math that I think was interesting. So again, the nice thing about a linear system like this is that estimating these filters A and B is nice. You can use a ridge regression. Ed has been using ridge regression very successfully over the years. We said, okay, let's use, Ed's framework here. We have a regularization. The closed form solution for H exists, so it's really quick to compute. But then coming up with a test statistic had some issues again. So we had to deal with biases again. So if you want to have a test statistic that tells you whether a link that you see between two sources in the brain is true or not, needs to be tested carefully. So it turned out that if we define a statistic that has a classic term of Granger, T times log ratio of the variances, T is the duration of the data. Again, we need to do some bias correction, and we had to derive these new formulas for bias correction for ridge regression. So I think this seems like a simple problem, but it had never done before. So they look long, but all of them are functions of the data, the covariate matrix, the TRF. So you can plug in your estimates in these formulas. It gives you a full bias, a reduced bias, you subtract and add. And then you get a statistic, and we showed that this actually gives you the same chi-square framework that I talked to you about. So we can come up with tests, really sharp tests to detect whether a link exists or not. So we did a bunch of simulations. Again, this is, the A matrix, the internal dynamics is a random matrix with plus minus 0.05. And the TRF was, the elements of TRF was random IID, so we had noise like TRF. And 2 of the elements, the 5th element of the TRF and the 2 element of the connectivity intrinsic dynamic matrix, we set them to 0, exactly to 0. And this is the model estimation. So the model, in fact, exactly detects them as 0 and detects everything else as significant, which is exactly the ground truth. And we changed the size of the network. So this was done in a 6 by 6 matrix. We did a 60 by 60. Again, it's striking that you exactly detect the 0 here and here, and everything else, you detect the effect. So it shows you that if you design the right test, the right statistic, the right thresholds, you have the optimal statistical power and low false alarm. So, and then, Lucas, being Lucas, did a lot of sanity checks. So he changed, I think some of it was Eimar's work, right? So Eimar was involved in that. So changing lambda, regularization, and seeing how the statistical power and false alarm change. So it seems like a very nice, robust method. Again, this is a more comprehensive simulation that we did. I'm going to skip this. This is another graphic of the same experiment Lucas showed you. So this is IEG, and the subjects were listening to videos. And what you see with MTRF, these are different channels and different lags, is that the MTRF gives you a filter like this. So again, some channels here and here show latencies around 200 milliseconds. Then you separate them in terms of a filter A and B in the var-X model. So you see that the filter A is detecting some internal dynamics. So the reason that they're looking like this 45-degree lines is that this is kind of a Toeplitz representation of A. So it shows that each channel has certain lags. And this is filter B, which is the TRF from which we take apart the contribution of internal dynamics. So again, as Lucas showed, it looks like this elongated MTRF response. In reality, if you believe that this model is a valid description, has a filter, a TRF-like filter with shorter latencies, but it's the internal dynamics that is making it kind of elongated. It's kind of a reverberation of this filter according to these taps that gives you this elongated filter. And if you combine these two, so the var-X model, the combined response is pretty much the same as MTRF. So again, you can recover the MTRF result, but the var-X allows you to tease apart the MTRF into two components, the internal dynamics and the feed-forward stimulus to response. So if you notice, there are two paras listed here, Lucas para and Vera para. So Vera is Lucas's elder daughter. She's a sociology student, PhD student at UC Berkeley, and I think Lucas was talking to her about this paper, and she said, "Oh, I have some cool data from labor, unions and strikes and all that." And we took her data and we analyzed this using the same framework. So, and we found something interesting that it's a finding in sociology. I don't know how valuable this is to sociologists, but it shows you that this method is somewhat versatile. So we found that if you look at the number of strikes by unions, and the number of workers on strike, the red curve, and number of workers that are participating in unions, and also the unemployment rate. These are, four variables, temporal variables from 1920 to pretty much now, I think 2019 or something. So we see a nice GC connection between them. So it looks like the driver is the unemployment rate. So the unemployment rate makes workers sign up for unions. They join unions, and when they join unions, that increases the number of strikes. And if there are more strikes, there are more workers on strike, right? So it looks like a trivial result, but we didn't imagine, we had no idea of the dynamics, social dynamics of this phenomena. So this came out of the var-X model. It's kind of nice. This is an econometric data. Again, one of Lucas's friends is an economy professor, and he gave us some data. Again, this is from Federal Reserve, about some, again, lots of variables that econometrists like to play with. So the message that I want to show you is that all these variables are highly correlated through years, right? So you can imagine that if you wanted to do functional connectivity between them, you see connections everywhere, right? So that's actually the correlation. But in reality, or I shouldn't call it reality. In the var-X reality, the connectivity between them is much sparser, right? So even though there are lots of correlated variables, not all of them are good predictors of each other. Some of them are confounds, right? So with this method, you can rule out many of them and, find something that is hopefully more meaningful. Okay, I think I kind of sped through the talk a little bit more, so I just want to conclude that maybe I can give you a break before so you can make room for the crab cakes, or just have more discussion. So again, the single message that I want to convey is that GC has nothing to do with causality. It's just a model selection for network data. And like all models, it's wrong. But if you apply it carefully, it can be useful. That's it. Thanks for your attention.
With the right way?
From our group?
Yeah.
Yeah, I think the 2022 paper, NLGC, that worked with Jonathan, I think.
Okay.
Yeah, sure. Yeah, let me go back, Rick. Also, the paper with Lucas, because we wrote it for the generalist audience, it's +1. So the first iteration didn't have any econometric or sociology data. So the reviewers said, well, you have a nice method, why don't you apply to non-neural data? And then, yeah, so that could also be a good introduction. So the +1 paper just came out a few months ago. And this one, let me go back. NLDC, the neuroimage paper from 2022.
I think when we ask authors, speakers to publish videos, we'll ask them to send us a link to the papers. So we'll put them on the CogHear website, we'll put a link to the videos that people have and one or two papers that are appropriate. So hopefully that'll be a good thing going, resource going forward. More questions?
Thanks.
How the temporal scale of either the video data, like specific frequency band, or the stimulus features that you're using, and what role does time constants play in?
Yeah, very good question. So one nice advantage of sparse estimation is that you can take a very long integration window as long as you want, but let sparsity pick up the relevant lags, right? So one thing that is a limitation of ridge regression is that you first need to set the number of lags or hopefully do cross-validation. Let's say I want to find TRFs of 300 milliseconds and then use ridge regression. But with sparsity, you can take a really long window, let's say a 5-second window, and the sparsity only focuses on the components that are relevant. Yeah.
More questions? More questions? Thank you. I need to play more with this, so I'm glad to.
Yeah. Thanks, everyone.